Yeah, I think almost all videos I have uploaded, lecture notes. Okay, so including these lecture notes, which is from this Eric Deman and Lyserson. Okay, so all these lecture notes. Okay, so these lecture notes plus videos that I have taken so far that have been uploaded in the Moodle. Perhaps you have got it and you are listening to it. Okay, and maybe from Sunday onwards I'll be posting the assignments also. Okay, so you keep an eye on that Moodle, and by the deadline you have to submit. Okay, so one deadline will be set, right? So by that deadline you have to submit. Okay, so we are discussing this divide and conquer, right? And in this divide and conquer we have discussed many algorithms so far, and one of the very interesting algorithms that we have discussed in the last class, it was this Karatsuba. Okay, Karatsuba. And right now we will discuss one algorithm for computing this a power n, okay, a power n calculation, and this is from this 2005 course of Eric Deman and Lyserson. Okay, so a power n calculation, say you have to calculate this 2 power 4. Okay, 2 power 4, here this a equal to 2 and this n equal to 4. Okay, and so n is integer here, right? 2 power 4 we have to calculate, and now the idea is how to calculate that. So naive algorithm will be taking order of n time. So you know, whenever I am calculating 2 power 4, the naive algorithm, what we do is we multiply 2 times 2 times 2 times 2. Okay, so how many number of multiplication? Maybe 1, and then what is the result? With that I'll be multiplying this one will be coming into picture, 4 times 2, and then maybe this 8 times 2, again this will be coming, so that will be 16, right? So this, if n equal to 4, how many number of multiplications we need? Can you tell me, anybody? N number? Everybody agreeing with that fact? N or n minus 1 or order of n, what? So how many exactly here in this case? How many multiplications we need? 4 multiplication. So 2 times 2, that is 1. Okay, that is 1 here, and then the result, and then 4 times 2, that is another 1. So this is number 2 multiplication, and then 8 times 2, it is 16. So it is how many multiplications necessary? N minus 1. Okay, so this is exactly n minus 1, and if we are not sure, maybe n or maybe n plus 1, maybe n minus 2, n minus order of n. Okay, so order of n is a very intelligent way to tell that how many number of multiplications are necessary without going into the exact case. Okay, we can approximate with this order of n. Okay, so this n minus, oh, I'm not audible. So previously I was audible. Okay, okay. Okay. So this n minus 1 number of multiplications necessary. So that's why they are telling, okay, this naive algorithm is taking theta n time or order of n time, right? Okay, now the mantra we have to chant that can we improve? Okay, can we improve? So the idea is definitely maybe we can improve. Okay, so the answer is yes, we can improve, right? So what is the idea we have to apply here? This divide and conquer paradigm, right? So the idea is telling this a power n, say this n is even, so this n is even here 4, so then we can divide this multiplication in terms of 2 n by 2. N by 2 means 4 by 2, that is 2, times 2 n by 2, that is 2. So 2 square times 2 square. So we can divide this this a power n calculation, we can divide this in terms of this. Okay, now what I have to do is, you see this, if I can calculate, say this 2 power 2, so if I am multiplying 2 power 2, that is 4, okay, right, 2 square, and then I don't have to calculate this 2 power 2 square, that is 2 times 2 again. That will be coming as free. Okay, so 4 times 4 I'll be getting, that is 16. So in this case, so this this might be needing only one multiplications, and then this will be coming as free, that is already I have computed the value of this, and then I'll be plugging that value here. And am I audible? Okay, am I audible? Okay, am I audible now? Am I audible now? Okay, okay, so this is one multiplication will be necessary here, and this will be coming as free, that I was telling. Okay, and then another multiplication will be necessary, 4 times 4. So in this case, if we apply this divide and conquer, okay, then we will be needing 2 multiplications instead of that 3. Okay, so for larger and larger number, this maybe if I am multiplying 2 power say 64, this 2 power 64 is a gigantic number. 2 power 64. So then we can feel the real difference between this naive approach and this divide and conquer approach. Okay, so you deal with this 2 power 64 calculation whenever you will be implementing this algorithm in your code. Okay, so this, if n is even, is this, and if n is odd, then we have to separate one a here, and then it will be becoming even again. Okay, so that way we have to, else part if this is n is even, or else this is odd. Okay, so in one iteration either this will be activated or this will be activated, right? Okay, so this is the way we can apply this divide and conquer algorithm. And in this case, you see this, we have only one part I have to recurse, only one part I have to recurse, other one will be coming as free. One part I have to recurse, the other one will be coming as free. Okay, so this Tn by 2, that is in one part I have to recursively solve one part, and then divide and combining operations, divide and combine. So this combine operation will be needing only one arithmetic operations here, two arithmetic operations here, so it will be theta of n. Okay, so in this case Tn will be equals to theta of log n or order of log n. So this already we have seen the recurrence. This is the binary search recurrence. Okay, Tn equal to Tn by 2 plus theta 1. Okay, theta 1. So this is constant, right? Theta 1. So Tn equal to order of log n. That is binary search recurrence. So it is easy. And you solve this using substitution method in your, whenever you have some kind of leisure time. Okay, okay, now I'll be discussing another one. This will be showing again this e power n calculation will be coming into picture at some point of time. Okay, so these Fibonacci numbers, right? Fibonacci, and this guy Fibonacci was a great mathematician. Okay, and you see this little bit history might be good here, because this Fibonacci changed the course of the game. Okay, so this, you see this ancient Europe, and in that part of the world that mathematics flourished, maybe that Archimedes, then this Euclid and all these guys. Okay, Pythagoras, this Pythagoras, this is 600 BC. Okay, so almost 2500 years back. Okay, so these guys laid the foundation of some mathematics, and before that some others were there, but notably they were at that time contributed so much. Okay, then you see it was flourishing on and on in that part of the world. Okay, and then maybe the dark age began for the Europe, maybe after the Christ. Okay, maybe. Okay, in that part the mathematics were at the backstage at that time, maybe 1st century to up to say 1000 or 1100. Okay, so this almost these 1000 years we didn't have so much contribution from Europe. Okay, as far as mathematics were concerned, at that time this Indian subcontinent, they flourished. Okay, and then this zero invented. Okay, that was a great invention. Okay, and then this 0 to 9, so 0 to 9, these numerals came into existence. Okay, from this Indian subcontinent. Okay, and then from maybe 500 to 1000, so everything shifted to the Middle East. Okay, everything shifted to the Middle East. Okay, that at that time, this Al-Zabar, okay, Al-Zabar, he was a big mathematician, okay, and this algebra is coming from that name, and Al-Khwarizmi, okay, and from that name algorithm is coming, okay, algorithm is coming. So all these guys were from the Middle East. They took the charge, okay, and they, whatever this the foundation led by these from that European part, okay, so they took, and this Indian subcontinent, whatever foundation was laid down, that was taken by those mathematicians and researcher from the Middle East, and they wrote countless books, okay. They transformed the knowledge whatever gathered, and they wrote several books, and they contributed as well, some pioneering contributions, okay. So what we are getting is this, it started from that part, then Indian subcontinent, then going to the Middle East, and now from 1100 this guy is coming almost around that part, this Fibonacci, okay, and what he did was excellent, okay. Whatever foundation these European guys, this Indian subcontinent, that was taken to this Middle East, okay, and they documented everything, they contributed pioneeringly in some areas, okay. So all that information gathered by a single man called Fibonacci, okay, and he wrote a book called Liber Abaci, okay, and then he transformed that knowledge again to the Europe, okay, and then on that pillar, this Galileo, Copernicus, and all those guys are coming, okay. So this maybe Leonardo da Vinci, all these guys are coming based on the foundation led by this Fibonacci, okay. So you see the history, this Fibonacci is a great guy, okay. Okay, so but he is mainly remembered to the community by his number, Fibonacci number, okay. So we are starting with 0, and then we are starting with n equal to 1, 1, okay. And then the F2 will be this 0 plus 1, that will be 1, then 1 plus 1, that will be 2, 1 plus 2, that will be 3, okay. So this is the recursive formulation, fn minus 1 plus fn minus 2, that you know already, okay. This, what is this Fibonacci number? From the first year onwards you are getting this, okay, but you are not knowing this history, okay, and who this Fibonacci was. And one of my favorite characters is this Fibonacci, okay, because of his legendary work like this, okay. A man single-handedly converted everything, okay. This is remarkable. Okay, so this Fn, this nth Fibonacci number, we have to compute nth Fibonacci number, and the question is how. So you know, see this, I can add up all these numbers one by one, 0, 1, and then again I am adding 1 plus 1, and then again I am adding this, okay. So this way possible, right? And there are other recursive algorithms, okay. So this phi, this is the golden ratio. I'm not telling about the golden ratio right now, so this will be a little bit digression from the course, okay. So with this phi golden ratio, okay, 1 plus root 5 by 2, and if we are calculating this 5 power n with that nth, say we have to find out, say 64th Fibonacci number, like this, and then this this algorithm might be taking this some omega phi of n. Okay, so that how it is taking I am not discussing right now. Okay, but our idea is not exactly, I will not be focusing here. Okay, so the main focus is that how can I improve. Okay, how can I improve this thing? And you think of a bit regarding golden ratio, and then how this naive algorithm is taking this omega phi of n, phi power n. Okay, so that you think, and why this is not good, that you also think. Okay, if you are not getting, then I'll be discussing. Okay, everything I should not be telling, but if you are having trouble understanding this after thinking, then I'll be helping you, because this golden ratio is again one of my favorite ratio. Okay, there is a lots of story behind that. Now the thing is that, so this computing Fibonacci numbers, so this again that I was telling, this computing this 1 by 1 sum f0 plus f1, then with the sum, if I am summing f2, then with that result I am summing f3. So each number, forming each number by summing the two previous, that will be taking theta n time. That will be taking theta n time. Okay, so now the idea is, can we improve? Can we improve? So the idea is, yes, we can improve. And the idea here is that this theorem, okay, this theorem is responsible for this. Okay, so this is called recursive squaring algorithm for Fibonacci. For Fibonacci number calculation, nth Fibonacci. This is recursive squaring algorithm. Okay. So this this is our maybe this f1, this is our f0, right? And you see this guy is telling this is f1 and this is f2. So f0 plus f1, that is 1 plus 0 is 1, so that is f2. Okay, so that's why it is written fn plus 1, that is our f2. Okay, that means here n is 1, right? So this is f2 plus f1, f0 and f1. Okay, that we can represent with this 1 1 1 0. And now if 1 1 1 0, if I am multiplying with this, say if I am taking, say, n equal to 2, if I am taking, so this 1 1 1 0, if I am doing, right? So can you tell me what should be the answer here? So this is 2 by 2, right? 2 by 2 matrix, this guy, and this guy is also 2 by 2. So what will be the dimension here? Can anybody tell the dimension of this matrix? 2 by 2, 2 by 2, 2 by 2, okay, 2 by 2. So now can you tell me what could be the number here? 2. So this row and this column, if I am multiplying and adding, 1 times 1 plus 1 times 1, this is 2. And this is 1 times 1, 1 times 0. So it will be 1, I guess. and then this one, 1 times 1, 0 times 1, so it is 1. So this will be 1 times 1, 0 times 0, so this will be again 1. So you see, this is our this is which number? So f0 is 0, f1 is 1, f2 is 1, f3 is 2. So you see, this is f1 and f2. Okay, so this is our f2, this is our f1, this is our f2, and this is our f3. Okay, so when n equals to 2, so then we are getting this, and from there which Fibonacci number I want, I can pick up. So then again, if I am multiplying this with 1 1 1 0 again, so if this is n equals to 3, then it is a power n calculation. Okay, a power n. So you see, this is our a, 1 1 1 0, it is our a, and then it is powering by a power n. So already we have seen that this calculation is taking order of n time or theta n time. Theta log n time. Theta log n time. Already we have seen that, right? So this is recursive squaring of this by this theorem. This fn plus 1, fn minus 1, that is 1 1 1 0 whole power n. Okay, so this is the theorem. Okay, there is this recursive squaring, that will be time theta log n, because we are calculating nothing but a power n. Okay, and we have seen already that a power n calculation will be taking, by divide and conquer, it will be taking order of n time or theta n time. Theta log n time. Order of log n time or theta log n time. Okay. So here the proof of the theorem by induction on n. Proof of the theorem, this will be calculated. We are claiming that this is the theorem, but where is the proof? Okay, so we are using the induction on n. Okay, if n equals to 1, we know this is naively true. Okay, 1 1 1 0 whole power 1, so that is 1 1 1 0, and we have seen already this is f2, this is f1, this is 1, this is 0 by definition. Okay, so this is passing, the base case is passing, and then inductive step. Okay, so we have to assume that it is true for some lower values of n. Say it is true for this n minus 1, so then I am getting 1, so this guys will be 1 1 1 0 whole power n minus 1, and now I am starting from here. So if I am starting from here, and then what I am getting, I can split this into the product of this fn minus 1, because if fn minus 1 times this, if I am doing, then what I will be getting, can you identify? If this column and this row and this column, if I am multiplying, then which element I will be getting? Fn plus 1. Okay, so that will be getting, and if I am multiplying this with this, then I'll be getting fn. Okay, so we can split this into this, and then as I am assuming that this is true for n minus 1, so I am plugging that value here. So that will be, this is a power n minus 1, by that indices I am getting, this is a power n. Okay, so a is 1 1 1 0. So that is we have proved. we have got the proof, right? We have got the proof. So this is for a power n calculation, and this is a very powerful algorithm, and that we can have several different applications for this. That's why I have introduced it. Okay. Okay. So this one more discussion today we'll be doing. That is, we will start discussing this one. This one is there in the syllabus. This is called order statistics. Okay, this is order statistics, and this is in CLRS book, and this is again from this Eric Demen and this Lyserson, that course 2005, and their lecture notes. Okay, and the CLRS book, this order statistics is discussed in chapter number 9, I guess. Okay, chapter number 9, and they have taken from their book. Okay, so this is the book. Okay, so now what this order statistics is, we have to find out kth smallest element or ith smallest element. So I have to find out this ith smallest element of n elements. Okay, and the list is unordered. List is not ordered. If the list is ordered, then the problem is very trivial. Okay, very easy. If the list is unordered, okay, say unordered list, we are having 13, 5, 9. So this is unordered list. Okay, and then I have to find out the ith smallest element. So you see, which is the first smallest element here? So 1 is the first smallest. Which is the next smallest element? The second smallest. Can you identify? 5 is the second smallest. Okay, second smallest. Second smallest element. Right. Second smallest. And what is the third smallest? This is 9. What is the fourth smallest? This is 10. And what is the fifth smallest? That is 13. So fifth smallest is the maximum element. So we can, instead of telling that this is the 13 is the maximum element, I can also say that this is the fifth smallest element. Fifth smallest. Fifth smallest element. So now the question is that how can I find, given this unordered list, how can I find this ith smallest element from the list? Ith smallest element. Okay. Ith smallest element from the list. That is the question. So this is the problem. And as you see, this I equals to 1, that is the minimum, and I equals to n, that n equal to 5 here, n equal to 5 here in our example. So that is the maximum element. That is the max element. Okay. And what is the median element? Okay. So if I sort this, 1, this will be 1, 5, 9, 10 and 13. Right. So this the middle element of this is called the median. Is called the median. Now, is there any question coming to your mind if I am saying that this is the median? You have to ask a question. Who will be asking a question? Yes. Who are you? Saurabh. Very good. That is the question. If the number of elements are even, then what we should be doing? Okay. So if another number is there, say 15, another number, then we are having two medians. Okay. One is this. Sorry. No, what is your question? Are you asking a question or you are telling some kind of answer? Okay, okay. Ah, so in that case, we are having two medians. Okay, so this is 9 one and 10 is another. So this is called the lower median. This is called the lower median, and this is called the upper median. Right. So we are having two medians in that case. So this, you see, that is why this I is defined. I is defined with this or this. Okay. If I am defining the median this or this, then we are addressing both the lower median and the upper median. Okay. So let us take the example that if the n is odd. So in that case, if this is n equal to 5, so 5 plus 1 by 2, that is 3. 5 plus 1 by 2. And it is also 5 plus 1, 6 by 2, that is also 3. So if odd, then we are having only one median, because both the n plus 1 by 2 floor and n plus 1 by 2 ceiling, both will be resulting the same number. But if n is even, so n is even, here n was 6. Okay, so then 6 plus 1 by 2, and if I am taking floor, what will be the value? What will be the value? 3. And what will be the value? 6 plus 1 by 2, 4. Yes, it is ceiling. Which one? 3. Who is telling 3? Okay. I got it. So 6 plus 1 by 2, that is ceiling, that is 4. Okay, so you see, this is the third one and this is the fourth one. As I mentioned that 1, 2, 3, so this is the third one, this is the third one, and this is the fourth one. So this, if I am defining this way the median, then I am getting everything right, everything in place, right? When n will be odd, only one median. When n will be even, two medians we are getting. Okay, so if I am trying to find out the unordered list, if I am trying to find out that what is the ith smallest element, then what will be coming to your mind? Which algorithm? Who will be telling? Who will be telling? Knockout tournament. Okay, that could be one possibility. Very simple one. Okay, so that is written over here. Okay, very simple one. So what we got to do is we have to sort the elements and return that index. Okay, we have to sort the elements and return that index. So here I have sorted it: 1, 5, 9, 10, 13, 15. And now if you are telling that, okay, you give me the fourth smallest, then fourth index position, the element of so first, here I am assuming that without repetition I am addressing this problem first. Okay, then repetition could be addressed by employing some other thing. Okay, that we can discuss afterwards. Okay, but that is a very good question, that if I am having repetition, then what will be happening? So if 4, if I am having 5, 5, 5, 5, all 5s. So if then in that case, what will be happening? 5, or here maybe 50. Here maybe 15, 20, something like this. Okay, so that could be easily solvable. Okay, but first of all, let me address this issue that if all the elements are distinct. Okay, so now this thing will be coming into picture, that we have to sort this and we have to find out the ith smallest element. We have to return that index position. So in that case, what will be the time complexity of our algorithm? So you see, the time complexity, the sorting will be taking theta log n log n time. Okay, and then returning that index position will be taking theta 1 time. So then theta n log n plus theta 1, it is theta n log n. So this they are telling, okay, using merge sort or heap sort, not the quick sort, we can do this theta n log n time we are getting. Okay, so this is the median. Median is also some smallest element. Median is also some smallest element. So that if so, either this n plus 1 by 2 2th smallest, or n plus 1 by 2 ceiling smallest element is the median. That you have to remember. Okay, so if I am telling the algorithm that we are trying to address, so this here we are getting that it is taking theta n log n time, right? And the mantra we have to again chant that can we improve? Can we improve? Right? So the answer is yes. Anybody having any idea about why it is yes? Do you know any kind of such algorithm? Anybody? Any one of you? Okay. So that is this is a Google question. Okay, so you have to, those who will be preparing for Google, Amazon, Microsoft, they will be knowing this algorithm. Okay, the ith order statistics or ith smallest element that we can find out in worst case order of n time. Order of n time algorithm is existing for this, and that algorithm we will be discussing. That algorithm we will be discussing in our course. Okay, so today we have seen the Fibonacci numbers. This the first we have seen that e power n calculation, then this Fibonacci number, nth Fibonacci numbers, and then we are seeing that ith smallest element, ith smallest element. So these three, already two we have discussed and three I have started right now. So today up to this, and in the next class we will be seeing that how we can improve this algorithm, theta n log n time algorithm, and we can propose one order of n time algorithm or expected order of n time algorithm. That expected analysis we will not be doing right now. Expected analysis that I do in some MTech class, and this but I'll be touching how we can compute this in, that's probability will be involved, expectation, expected running time, order of n. That's a very simple naive implementation. And another one is this deterministic order of n time algorithm without involving some random number generation. We can solve this with order of n time. So that algorithm we'll be discussing and we'll be analyzing in the next class. Okay, so if you have any question now, you can ask me that question, but let me take your attendance first. Okay. So I have taken your attendance. Now you can leave if you don't have any question. If you have question, you can ask me. Thank you. Thank you.